That map in your hands is already wrong. The lines we draw are temporary illusions, and nature holds the permanent pen. This is the story of how our planet constantly rewrites the maps we thought were fixed. We will travel to coastlines that have retreated, cities submerged by the sea, and rivers that have abandoned their ancient beds. By the end, you will see every border and landmark not as a fact, but as a fleeting snapshot in Earth's deep time. We will uncover how entire civilizations have vanished beneath the waves and why the ground under your feet is not as stable as it seems. What does it truly mean to live on a world that is always remaking itself? Gerardus Mercator never intended for his 16th century world map to become a classroom standard. He crafted it for sailors, a tool to plot straight lines across a curved ocean. Yet this single projection, with its distorted continents and enlarged northern lands, became frozen in time as the definitive image of our planet. It is a perfect example of a map as a snapshot, capturing not eternal truth, but one man's solution to a navigational problem, framed by the knowledge and biases of his era. For centuries, we have treated maps as symbols of human mastery, believing the lines we draw are as permanent as the paper they are printed on. But a map is a fragile thing. It prioritizes what its creator deemed important, whether trade routes or political borders, while completely ignoring the slow, powerful forces already at work to change the landscape. Geographer Marc Monmonier reminds us that all maps are distortions by necessity. They must lie to tell a certain truth, and in doing so, they create an illusion of stability. A desert map from a century ago shows fixed dunes, but the sand is always on the move, sculpted by winds that pay no heed to our charts. A map detailing a river's course is outdated the moment the ink dries, as the water patiently carves a new, meandering path. How many historical maps of your own hometown would you find utterly unrecognizable if you tried to walk their streets today? This realization cracks the foundation of our assumed certainties. It forces us to ask what else we accept as fixed that is, in reality, constantly in flux. So what are the specific, unstoppable forces that wield nature's eraser and begin this process of rewriting the world? The ground beneath your feet is drifting right now. The supercontinent Pangaea began to break apart over 200 million years ago, but that breakup is far from over. The continents are still moving, carried on immense tectonic plates at roughly the same speed your fingernails grow. This slow motion dance, driven by the planet's internal heat, is a fundamental force that rewrites our world map over deep time. Coastlines are stretched and fractured, new mountains are thrust skyward, and the very arrangement of oceans is altered, which in turn shifts global climate patterns over millennia. The scientist Alfred Wegener first pieced together this puzzle in the early 20th century, noting how the coastlines of South America and Africa fit like pieces of a jigsaw, and how matching fossil records were found oceans apart. His theory of continental drift was met with fierce skepticism, yet today, plate tectonics is the bedrock of modern geology. It explains not just the distribution of continents, but the very nature of earthquakes and the ring of fire where volcanoes are born. This force is both creative and destructive. It forges new land in monumental collisions, like the ongoing thrust of the Indian plate into the Eurasian plate that continues to push the Himalayas upward by a tiny amount each year. Yet in subduction zones where one plate slides inexorably beneath another, ancient seabeds are dragged back into the planet's molten interior. What does national sovereignty mean when the territory it claims is literally moving, inch by inch, year by year? It reveals a profound truth that our political lines are drawn on a canvas that is itself in constant, slow motion. And while the planet's internal engine reshapes the stage, another powerful artist is at work, using the fluid and relentless power of water to carve entirely new realities. A river never holds the same course for long. The Mississippi River, a serpent of water and sediment, has shifted so profoundly over centuries that towns which once buzzed with riverboat traffic now sit quiet and landlocked, separated from the waterway that gave them life by miles of new land. This is the work of river meandering, a slow, persistent dance where water erodes the outer bank of a bend and deposits silt on the inner bank, causing the river's path to wander across its floodplain like a loose garden hose. Over decades, a gentle curve can become a horseshoe bend, and eventually, the river may simply decide to take a shortcut, abandoning its loop entirely in a sudden event called an avulsion. This process completely rewrites the local map, rendering old charts useless and creating new islands and peninsulas from the accumulated silt. Hydrologists who study these dynamic systems understand that a river is not a line but a system, a living entity that breathes and shifts. Our attempts to control them through levees and channels often backfire in unexpected ways. By confining a river like the Mississippi with walls, we prevent its natural flooding and sediment deposition, which starves the downstream delta of the material it needs to rebuild land, actually accelerating its subsidence into the sea. This same story has played out for millennia with China's Yellow River, whose mouth has jumped hundreds of miles over recorded history, repeatedly inundating vast agricultural plains and redrawing the boundaries between provinces, forcing entire communities to pick up and move. Political lines drawn on a map mean very little to the water that carves the actual landscape. Have you ever traced a river on a modern map only to find an oxbow lake or a ghost channel nearby, a silent testament to its former path? Rivers are nature's most persistent cartographers, teaching us that the only constant in geography is change itself. And as these rivers empty into the ocean, their sediment builds the most transient and contested lands of all, the constantly shifting coastlines. A historic lighthouse at Cape Hatteras no longer stands where it was built. The ocean crept so close that the entire structure was picked up and moved inland, a dramatic retreat from a changing shoreline. This is the daily reality of coastal erosion and accretion, where land is both taken and given by the sea. Waves and currents act as nature's sandpaper, constantly grinding away at cliffs and beaches, while in other places, those same currents drop their suspended sediments, building new land grain by grain. Geomorphologists who study these shape-shifting coasts document a world in flux. The iconic white cliffs of Dover, for instance, are steadily diminishing, their chalky faces crumbling into the English Channel with each passing storm. Meanwhile, far away in the delta of the Ganges and Brahmaputra rivers, new islands known as chars emerge from the water, born from the immense load of silt carried down from the Himalayas. Human intervention often speeds this entire process up. Coastal development removes protective dunes and wetlands, while sand mining for construction starves beaches of their natural replenishment. Nowhere is this loss more starkly visible than in Louisiana, where the coastline is vanishing at an almost unbelievable rate. On average, a football field's worth of land succumbs to the water every single hour. Maps of the region's intricate bayous and marshes become obsolete within just a few years, their carefully drawn channels and islands simply gone. What beloved beach from your childhood memories has already narrowed beyond recognition? This relentless reworking of our edges makes a mockery of permanent maritime boundaries. As the ocean claims and creates land, another, colder force is carving the planet on a monumental scale, one that operates with the patient, crushing power of ice. Ice is a sculptor of continents. The immense ice sheets of the last glacial period did not simply cover the land, they reshaped it, carving out the basins that would become the Great Lakes and grinding the deep, dramatic fjords of Norway. A glacier is more than frozen water. It is a colossal force of erosion and construction, a river of ice that flows with imperceptible slowness yet possesses the power to move mountains. As it advances, it scrapes and pulverizes the bedrock beneath it, and when it eventually retreats, it leaves behind a completely new world of sculpted valleys, scattered hills of debris called moraines, and vast deposits of sediment that redirect entire river systems. Glaciologists study these frozen archives, reading the layers of ice like the rings of a tree. They have documented how, during a period known as the Little Ice Age that lasted from roughly the 14th to the 19th centuries, glaciers around the world expanded dramatically, swallowing farms and villages in the Alps. Yet that expansion has now violently reversed. In our modern era of warming, the retreat is breathtakingly fast. Alpine maps from the early 20th century are now historical artifacts, showing white tongues of ice that have since vanished entirely, revealing new valleys and mountain passes that had been sealed for millennia. This is not just a story of mountain landscapes, but of global geography. The massive ice sheets covering Greenland and Antarctica are melting into the ocean, and this water raises sea levels for every coastline on Earth. The very act of melting ice in one part of the world redraws the map in another, drowning islands and forcing coastal cities to reconsider their future. If the great polar ice caps continue to shrink, how will future generations even depict the Arctic and Antarctic on a map? Will they be white continents or blue oceans? The slow, cold power of ice demonstrates that even the most gradual forces can unleash changes that are both swift and vast in their consequences. But the planet also holds a far more explosive and immediate cartographer, one that can build new land in a matter of days. In 1963, fishermen off Iceland's coast witnessed the impossible. The ocean boiling as a new island violently broke the surface. This was Surtsey, a territory born from a volcanic vent, a place that had never before existed on any map. Volcanism is nature's most dramatic cartographer, capable of building entire islands from the ocean floor or obliterating mountains in a single, fiery breath. It forges new land through relentless lava flows and the accumulation of ash and rock, while its destructive power can erase established features in an instant. When Mount St. Helens erupted in 1980, it did not merely cover the landscape in ash, it removed the entire northern flank of the mountain, reducing its height by over 1,000 feet and sculpting a vast, barren amphitheater where a forested peak once stood. The maps of the region became useless overnight, replaced by charts of a new, raw terrain. In stark contrast, the volcanic activity in Hawaii is a slower, more persistent act of creation. The Kilauea volcano has been steadily adding land to the Big Island for decades, its lava flows creeping into the sea, cooling, and solidifying into hundreds of new acres of black rock coastline. This new ground is instantly contested as scientists, the state government, and even native cultural groups debate who owns land that did not exist a generation ago. What new volcanic islands are currently forming on the seabed, waiting for the moment they will rise and demand a place on our world atlas? These fiery forces remind us that the planet's surface is a living, breathing canvas where creation and destruction are two sides of the same coin. And just as fire builds new land from the sea, another elemental force is tirelessly at work sculpting the earth in the planet's vast, dry expanses where the very ground is constantly on the move. The sand beneath your feet is never truly still. In the vast emptiness of the Sahara, entire mountains of sand are on the move, marching relentlessly across the landscape. These are not static features on a map, but slow-motion waves consuming everything in their path. Ancient caravan routes, once bustling with traders carrying gold and salt, now lie buried under meters of sand. Oasis settlements, those vital blue dots that guided travelers for centuries, can vanish entirely as the water table shifts or the dunes close in, only for new ones to emerge miles away. This is the work of aeolian processes, a powerful geological force where the wind acts as both a sculptor and a destroyer. It plucks individual sand grains from one place and deposits them in another, constantly redrawing the desert's intricate features. To uncover this lost geography, geologists and archaeologists work together, using satellite imagery and ground-penetrating radar to find legendary cities like Ubar, a hub of the frankincense trade that was completely consumed by the sands, its location a mystery for over a millennium. These shifting sands make maps of arid regions the most temporary of all. A chart showing a reliable water source can become a death sentence in a generation. How do the nomadic Tuareg or Bedouin peoples navigate such an impermanent world? They do not rely on fixed maps, but on a deep, generational knowledge of the wind's patterns and the land's subtle signs, understanding that the desert is a fluid, living entity. This natural migration is now accelerating into a crisis known as desertification, where climate change and human pressures like overgrazing cause fertile land to degrade and transform into desert. The Gobi Desert is expanding outward, its edges creeping into farmlands in China and Mongolia, swallowing villages and forcing governments to constantly redraw maps designating agricultural zones and habitable areas. The very definition of a nation's productive territory is shrinking under the advancing sand. If even the most barren and seemingly permanent places on our maps are in constant motion, what does that say about the stability of our coastlines? The ocean's edge is another frontier where the map is being rewritten, not by the wind but by the rising water itself. The ocean's reach has never been permanent. An entire country once thrived where the North Sea's waves now roll, a lost world known as Doggerland. For thousands of years, this was no myth, but a vast, inhabited landscape of hills, forests, and rivers that connected Britain to mainland Europe. Mesolithic communities hunted, fished, and made their homes on this fertile plain. Then, around 6,500 years before the Common Era, the rising seas finally won, swallowing the land in a slow, relentless inundation that transformed a territory into a seabed. This was not a unique catastrophe, but a regular feature of our planet's history. Sea levels rise and fall dramatically over millennia, driven by the melting of massive ice sheets and the simple fact that water expands as it warms. These fluctuations have repeatedly drowned entire continental shelves and exposed land bridges like Beringia, which allowed the first humans to cross into the Americas. The world map has been a fluid document, with coastlines advancing and retreating like tides on a geological scale. Scientists called paleogeographers act as detectives for these vanished lands. They use sonar to map the ghostly river channels etched on the seafloor and pull up core samples that contain ancient pollen and the bones of land animals, painstakingly reconstructing the geography of worlds we lost. Their work proves a humbling fact: many of our current coastlines are merely temporary high stands, a fleeting moment when the ocean has paused in its long-term advance. This ancient process has taken on a terrifying new urgency. Global sea levels are rising again, this time accelerated by human activity. For low-lying island nations like the Maldives, this is not an abstract geological concept but an existential threat. Their highest points are just a few meters above the water, and their very existence on the map is at stake. In places like southern Florida, coastal neighborhoods already experience routine flooding during high tides, a preview of a future where today's city grids become tomorrow's nautical charts. What ancient civilizations, what entire chapters of human history lie preserved beneath the waves, waiting for our technology to rediscover them? The constant flux of the ocean reminds us that the most fundamental lines on our maps, the coastlines themselves, are among the most transient. And just as the physical world is reshaped by water and ice, the living world wields its own powerful influence over the maps we create. Life itself is a cartographer, building land from the depths with the patient labor of countless tiny architects. Coral polyps smaller than a fingernail pull calcium from the sea and build it into limestone fortresses, creating the only living structures visible from space. This process of calcification constructs entire archipelagos, particularly the ring-shaped atolls that dot the tropical Pacific. Each atoll begins its life not as a coral reef, but as a volcanic island. As the volcano sinks back into the ocean floor over millions of years, the coral reef fringing its shores grows relentlessly upward, chasing the sunlight. What remains is a fragile ring of coral and sand, a lagoon where a mountain once stood, a landform born entirely from biological persistence. These atolls appear on our maps as stable dots of green, yet they are in a constant state of flux, a race between construction and erosion. The living reef on the ocean side builds the outer wall, while storms and waves grind the sand within. Marine biologists who study these systems see them as dynamic, breathing entities. The Great Barrier Reef, for instance, is not a single monolithic structure but a complex mosaic of thousands of individual reefs. Its growth patterns are exquisitely sensitive, expanding during favorable periods to expose new shoals that challenge navigators, or receding during stress, submerging features that were once hazards marked on nautical charts. The very maritime boundaries of nations can hinge on the health of a coral reef, as international law often defines territorial waters from these living foundations. For the people of the Maldives, this is not an abstraction. Their entire nation is built upon the work of coral. The habitable islands of each atoll exist only because the coral reef provided a foundation that trapped sediment and grew high enough to break the sea's surface. Their history, their culture, and their presence on the world map are gifts from the polyp, yet this gift is now being revoked. As ocean temperatures rise and the water becomes more acidic, mass bleaching events occur. The stressed polyps expel the symbiotic algae that give them color and energy, leaving behind a ghostly white skeleton. A reef can recover from this, but repeated stress leads to its death. A dead reef stops growing and begins to crumble, losing its battle against the waves. Without the living coral to maintain it, the very land it built begins to vanish, eaten away by the sea it once held at bay. How will future maps depict these island nations if the reefs that support them die? Will the Maldivian atolls be drawn as dotted lines, indicating lands soon to be lost, or will they simply fade from the atlas altogether, becoming modern-day doggerlands? The rise and fall of coral proves that biology holds a pen as powerful as any tectonic force. And just as these living structures can be buried by the sea, so too can the grandest works of human civilization be swallowed and then miraculously revealed by the shifting earth. The legend of Atlantis is a ghost story written in water. A philosopher named Plato first described a powerful, advanced civilization that in a single day and night of misfortune was swallowed by the sea and vanished. While no sunken marble metropolis has been found, the story feels hauntingly plausible because it echoes a truth our ancestors knew all too well, that the ground can betray you and the sea can reclaim everything. Geologists and historians now suspect the myth was inspired by a very real cataclysm, the colossal volcanic eruption of Thera around the 1600s before the Common Era. This explosion, one of the most powerful in human history, utterly shattered the island we now call Santorini and sent tsunamis racing across the Mediterranean. These waves would have slammed into the coast of Crete, devastating the sophisticated Minoan civilization, a sea power that ruled the waves and then, from the Greek perspective, simply disappeared. The memory of a whole culture wiped away by nature's fury could easily have warped over centuries into the tale of a lost continent. Atlantis is not a place, but a recurring human nightmare, the fear of a map being permanently and violently erased. This nightmare became reality for the people of Helike. In 373 before the Common Era, this prosperous Greek city-state was obliterated in a single night. An earthquake liquefied the ground, and a tsunami from the Corinthian Gulf finished the job, dragging the entire city and its inhabitants beneath the waves. For centuries, Helike was just a story, a cautionary tale from ancient texts. Then, in the 1980s, archaeologists finally discovered its remains, not on the seabed, but buried deep under layers of silt in a coastal plain. The land itself had shifted, hiding the evidence of its own destruction. How many other settlements, now marked only by a name in a dusty chronicle, lie concealed by a changed coastline or a river's new course? These events blur the line between geology and folklore, proving that nature's upheavals are so profound they become embedded in our very culture, a warning passed down through generations. If a city like Helike can vanish from both the land and human memory for thousands of years, it forces a humbling question about our own sprawling metropolises. Their permanence is an assumption, not a guarantee. And just as a single disaster can erase a city from the map, broader, slower shifts in the global climate have redrawn human geography on a continental scale. The Sahara was not always an ocean of sand. Just 5,000 years ago, its landscape was one of rolling grasslands, dotted with lakes and crossed by rivers where hippos and elephants roamed. This was the African humid period, a time when a slight wobble in Earth's orbit shifted monsoon patterns, watering what is now the world's largest hot desert. The evidence is etched into the rock itself, in cave paintings from Tassili and Naja that depict giraffes and cattle herders, scenes utterly alien to the barren plateau of today. Paleoclimatologists, the detectives of ancient weather, pieced together this story from fossilized pollen and the sediments of long-vanished lakes. They reveal a planet where the very climate is a cartographer, redrawing the map of where life can thrive. For millennia, the Green Sahara was a bridge, not a barrier. Human populations moved freely across its fertile corridors, their migration routes tracing a map of opportunity. Then the orbital cycle continued its slow turn. The rains retreated, the lakes dried up, and the desert began to reclaim its territory. The maps of human habitation crumpled at the edges, then tore in two. Populations that were once connected became isolated, their worlds shrinking as the sand advanced. This was not a sudden catastrophe, but a relentless, generations-long squeeze that reshaped civilizations by altering the very ground beneath them. Today, human-driven climate change is wielding that same power, but at a breakneck speed. Some arid zones may see temporary greening as weather patterns shift, while fertile breadbaskets face the threat of desertification. The agricultural maps we rely on, which show the wheat fields of North America or the rice paddies of Asia, are based on a climate reality that is already slipping into the past. As growing seasons shift and droughts intensify, the most productive regions on our maps could become barren within a generation. How do you draw a reliable border when the climate that defined it has moved on? This reveals the ultimate cartographic challenge. Our maps must now account for the invisible lines drawn in the atmosphere, not just the solid ones on the ground. And just as the slow creep of climate redraws the world, our planet also holds the capacity for a far more violent and immediate act of revision, unleashed by the catastrophic power of water. A single catastrophic flood can erase a landscape and replace it with another. In the dry expanse of eastern Washington, a geologist named J. Harlan Bretz stared at a geological puzzle in the early 20th century. He saw a vast, scarred land of deep, dry canyons, colossal potholes, and enormous gravel bars, a terrain he named the channeled scablands. His radical explanation was that this entire region, larger than some states, had been sculpted not by the slow grind of rivers over millennia, but by a titanic flood of almost unimaginable power. The scientific establishment mocked him, for he was challenging the very foundation of geology, which held that change was always gradual. Yet Bretz was right. Around 15,000 years ago, a massive ice dam holding back a prehistoric lake in Montana catastrophically failed. The result was a wall of water hundreds of feet high, racing across the plateau at speeds of 60 miles per hour. This was not a river, it was an inland sea in violent motion. It tore up the bedrock, carved channels 600 feet deep, and scattered house-sized boulders called erratics, hundreds of miles from their source. In a matter of days, it redrew the entire map of the region, creating a brand new geography that had never existed before. Similar events have scarred the planet. In the Altai Mountains of Siberia, another glacial lake burst its icy confines, scouring valleys and permanently rerouting entire river systems in a single, furious event. These mega floods force us to accept that our planet's history is not one of only slow, patient change, but is also punctuated by moments of breathtaking violence, where the map is not just revised but torn up and entirely redrawn in a geological instant. How many other seemingly ancient landscapes are actually the fresh scars of forgotten deluges? This sudden power of water reveals that nature's pen can move with the force of a sledgehammer. Yet the Earth does not only reshape itself through forces of immense power, but also through quiet, hidden collapses where the ground itself simply disappears from view. The ground can open up and swallow a house in minutes. In a quiet Florida neighborhood, a perfectly manicured lawn might suddenly give way, collapsing into a gaping maw that consumes cars, swimming pools, and entire living rooms. This terrifying phenomenon is a sinkhole, a stark reminder that the very earth beneath our most stable-seeming communities is often hollowed out. These events are not random acts of nature, but the final stage of a slow, invisible process that has been underway for millennia. They occur in regions built upon soluble bedrock like limestone, gypsum, or salt. Rainwater, slightly acidic from absorbing carbon dioxide in the atmosphere, seeps into the ground and begins to chemically dissolve this rock, carving out vast, hidden networks of caves and tunnels. This is the world of karst topography, a landscape defined by what is missing. For years, even centuries, the land surface remains stable, held up by the roof of these subterranean voids. But eventually, the weight becomes too much, and the ceiling collapses without warning, instantly rewriting the local map. Geomorphologists who specialize in these terrains act as cartographers of the unseen. They map vast hazardous zones in places like the Yucatan Peninsula in Mexico or the karst highlands of southern China, regions pockmarked with thousands of sinkholes known as cenotes or tankengs. These are not just small pits, some are colossal caverns that have consumed entire stretches of jungle or have filled with water to become new, deep blue lakes. A map of a karst region is never finished. A forested area marked on a map can vanish into a new sinkhole, or a new pond can appear where a farmer's field once stood. These collapses can be agents of both destruction and discovery. A sinkhole might expose a previously hidden cavern filled with pristine mineral formations, or it might unearth the bones of prehistoric creatures that fell in millennia ago. The very process that erases features from our maps can also reveal archaeological treasures, forcing historians and geologists to collaborate on a new understanding of the land. This constant hidden erosion challenges our most basic assumption of safety. How many undiscovered caverns lie in the dark beneath your own hometown, silently growing until the moment the surface can no longer hold? Sinkholes teach us that stability is an illusion, and that the planet's most dramatic revisions often begin with a single, dissolving drop of water. This hidden fragility finds a violent parallel in the sudden, world-shattering power of earthquakes, which can redraw boundaries not over years but in an instant. The Earth can rewrite its own coordinates in a single, violent shudder. During the Great San Francisco earthquake of 1906, the ground along the San Andreas Fault did not just crack, it slid horizontally, instantly shifting fences, roads, and property lines by up to 20 feet. In less than a minute, every pre-existing survey of the region was rendered obsolete, a collection of lines that no longer matched the reality of the land. This is the instantaneous power of seismic activity, where tectonic stresses that have accumulated for centuries release their pent-up energy in a flash, forcing immediate and dramatic revisions to our maps. The movement is not always a simple side-to-side shift. Fault lines can thrust one block of land upward, creating a new scarp or ridge, or drop another downward, which can divert the course of a river or permanently submerge a section of coastline. The very longitude and latitude of a location can be measurably altered by a major quake, as the planet's crust settles into a new, strained equilibrium. Seismologists now use networks of GPS sensors and satellite data to watch this slow-motion dance in real time. Their instruments reveal that entire regions, from the islands of Japan to the coast of California, are in a state of constant, creeping motion, locked in a tectonic struggle that guarantees future upheavals. This relentless movement makes our maps perishable goods, requiring constant adjustment just to stay vaguely accurate. The consequences of this cartographic violence were tragically illustrated by the 2011 Tohoku earthquake in Japan. The quake was so powerful it shifted the entire main island of Honshu eastward by over 8 feet. In a horrifying secondary effect, it also dropped sections of the coastline vertically, lowering them closer to sea level and allowing the subsequent tsunami to rush farther inland with even greater destructive force. The event was so profound that nautical charts had to be redrawn, as the depth of the seafloor and the shape of the harbor approaches were permanently altered. How does a society plan for the future when the very ground used to define its borders and build its cities is actively sliding away? Earthquakes are the most abrupt reminder that nature holds the final veto over our human geography. Yet, even in the absence of such cataclysmic violence, the planet is engaged in a quieter, more patient form of revision, where the very bones of the landscape are slowly worn down by the elements. The Appalachians stand as quiet, rounded giants today, their peaks a fraction of their former Himalayan heights. This is the slow, patient work of weathering, the planet's most fundamental act of revision. Every drop of rain, every cycle of freezing and thawing, and every tree root prying at a crack in the bedrock is part of this relentless process. Chemical weathering sees rainwater, slightly acidic from the air, dissolving the minerals that bind rock together. Physical weathering uses the expansion of ice in cracks and the sheer force of temperature changes to fracture solid stone. Over millions of years, these processes break down the mightiest mountain into soil and sediment, lowering peaks, widening valleys, and softening the sharp contours you see on a topographic map. Geologists who measure these rates understand that a landscape's lifespan is dictated by its climate and composition. In the warm, heavy rains of the tropics, limestone can dissolve so quickly that the very ground seems to melt away, creating dramatic sinkholes and jagged karst towers. In contrast, the dry, cold air of a desert preserves rock formations for far longer, slowing the chemical reactions that cause decay. The iconic, stark silhouettes of Monument Valley are a perfect testament to this uneven erosion. Those isolated buttes and mesas are not features that were built up, but rather what remains after wind and water meticulously scoured away a once vast, continuous sandstone plateau. They are the final, crumbling pages of a geological story whose earlier chapters have been completely erased. What famous landmarks from the Sphinx to Mount Rushmore are currently surrendering grain by grain to this invisible, inexorable force? Weathering teaches a profound lesson in patience, demonstrating that even the most permanent seeming features are merely temporary in the deep time of our planet. This gradual dismantling, however, can set the stage for a far more sudden and dramatic act of cartographic revision. When the balance fails, entire slopes can give way in an instant, remapping the local geography with terrifying speed. A mountain can walk in a single, terrifying moment. In 2014, a rain-soaked hillside near Oso, Washington, gave way without warning. An entire slope of saturated soil and rock rushed across the valley, traveling at incredible speeds. It buried a neighborhood, blocked the North Fork of the Stillaguamish River, and within minutes created a new, brutal geography. A river was dammed, a lake formed where none had been, and the local map was rewritten by an avalanche of earth. This catastrophic event is a stark example of a landslide, a process geologists call mass wasting, where gravity finally wins its long, patient tug of war with a slope. These are not slow erosional processes, but rapid, violent collapses that can be triggered by an earthquake shudder, a period of intense rainfall that lubricates the ground, or even human activity like deforestation or construction that undercuts a hillside's fragile support. The result is the complete obliteration of the existing landscape. Forests, roads, and homes are scraped away, and in their place, a chaotic jumble of debris is deposited, forming a new hill, a new valley, or a new body of water. Geotechnical engineers meticulously analyze the scars of such events, studying soil composition and slope angles to create hazard maps that predict which areas are most vulnerable. They look for telltale signs like curved tree trunks or small ground cracks that hint at a slope's slow, creeping movement, yet nature retains a formidable element of surprise. A slope can appear perfectly stable for centuries, its internal structure secretly weakened by groundwater seepage, until one final, triggering drop of rain causes it to fail. This is a constant, grim reality in the Himalayan foothills, where monsoon rains regularly loosen the earth, sending massive landslides down onto villages and roads, often isolating entire communities and forcing emergency remapping of vital supply routes. These events can do more than just alter the physical map. They can bury historical sites under tons of rubble, erasing cultural landmarks as effectively as any invading army. So how can we better predict which seemingly solid hill is next to surrender to gravity? Advanced technologies like LiDAR, which uses lasers to map the ground surface in exquisite detail, can reveal ancient landslide deposits and subtle ground movements invisible to the naked eye. But the fundamental lesson remains. Landslides demonstrate that gravity is a relentless, patient cartographer, constantly redrawing our steepest terrains. And as the ground gives way in these dramatic collapses, another, more insidious shift is occurring in the planet's frozen north, where the very ground that has been solid for millennia is now turning to mud. The ground is literally softening beneath our feet in the Arctic. Across the vast Siberian tundra, a great thaw is underway, transforming the very foundation of the landscape. Permafrost, ground that has remained frozen for thousands of years, is now melting. This is not a gentle process. As the ice within the soil turns to water, the land loses its structural integrity, collapsing into a chaotic, waterlogged terrain of sinkholes and depressions known as thermokarst. From above, the change is dramatic. A patchwork of new, oddly shaped lakes appears where solid ground once existed, blue scars on a map that is being rewritten in real time. Climate scientists monitoring this transformation watch as ancient drainage patterns are completely rerouted. Water that once flowed over frozen earth now seeps into the collapsing ground, creating new channels and drowning ancient forests. The very coastlines are crumbling as the ice-rich cliffs, no longer cemented by permafrost, are rapidly eaten away by waves, causing islands to vanish and new bays to form where none existed on nautical charts from just a few decades ago. This is more than a geological curiosity. It is a direct threat to human habitation. In Alaska, the village of Newtok is being systematically dismantled and moved to higher ground, its original location succumbing to relentless erosion from the thawing ground. The people who have lived on this land for generations are becoming climate refugees, forced to relocate because the map beneath their homes is dissolving. What does it mean for a community when the land it is built upon can no longer be trusted? The thaw also unlocks a more insidious threat. Trapped within that frozen ground are vast stores of methane, a potent greenhouse gas. As the permafrost melts, this gas is released into the atmosphere, creating a dangerous feedback loop that accelerates the very warming that caused the thaw in the first place. The transformation of the Arctic is a stark, visible signal of the accelerating pace of environmental change, proving that even the most solid and frozen places on our planet are transient. And just as the physical ground can be reshaped by a changing climate, the living fabric of a landscape can be rewritten by a single, introduced species. A single plant can redraw a map. In the American South, a vine called kudzu, introduced with good intentions for erosion control, escaped cultivation and began its silent conquest. It grows a foot a day, smothering entire forests, draping telephone poles, and swallowing abandoned cars in a relentless green wave. From a satellite's view, the transformation is stark. A uniform, deep green blanket has replaced the complex, mottled patterns of a diverse ecosystem. This is biological invasion, a force of cartographic change driven not by wind or water, but by life itself. When a non-native species arrives in a new land without its natural predators, it can remodel the entire ecosystem. The cane toad, brought to Australia to control pests, became a pestilence itself, its toxic body decimating native predators and altering the food web across vast stretches of the outback. In the Great Lakes, tiny zebra mussels, arriving in the ballast water of cargo ships, have colonized every hard surface in such dense numbers that they have clarified the water by filtering out the plankton, which in turn allows sunlight to reach deeper, encouraging new plant growth and fundamentally shifting the lake's ecology. These changes are not merely biological, they are geographic. Dense stands of invasive trees can suck water tables dry, turning seasonal streams into dry gullies. Other invaders can alter soil chemistry or change fire patterns, making a landscape more flammable. The very resources that define a region on a map, its water, its fertile soil, its timber, can be rewritten by an introduced species. As the global climate continues to warm, these invasions are accelerating. Warmer temperatures are pushing species poleward, creating new corridors for migration and allowing tropical invaders to gain a foothold in temperate zones. The maps of tomorrow will need to account for these shifting biomass, showing where forests have been transformed into thickets or where fisheries have collapsed due to a new competitor. The living world is not a passive backdrop for our maps, it is an active, often disruptive co-author. And just as a tiny mussel or a fast-growing vine can reshape a continent's edges, our planet has also experienced revisions from a source far beyond its atmosphere, where the map is rewritten in a single, fiery instant from the sky. A meteorite impact does not just leave a crater, it forges an entirely new landscape. The famous Barringer crater in Arizona is a vivid scar, but it is a small sample of the cataclysm that created the Chicxulub crater beneath the Yucatan Peninsula. That impact 66 million years ago did more than excavate a hole. It triggered a global winter, caused mega tsunamis that rewrote coastlines across the Gulf of Mexico, and is credited with the mass extinction that ended the age of dinosaurs. In a single day, the ruling architecture of the planet's ecosystems was erased, and the biological map was reset, allowing new forms, including mammals, to rise to prominence. The geography itself was permanently altered, with the crater's rim influencing groundwater flow and creating a unique ring of cenotes or sinkholes that still define the region's hydrology today. Such events are the ultimate demonstration of nature's power to revise, proving that the pen that redraws the map can sometimes fall from the stars. The Chicxulub impact did not just end an era, it engineered a new world. When that asteroid, miles wide, slammed into what is now Mexico 66 million years ago, it unleashed energy billions of times greater than an atomic bomb. The immediate effects were apocalyptic, but the long-term cartographic changes were just as profound. The impact excavated a crater over 100 miles wide, its center sinking deep into the Earth's crust while its outer rim rose in a colossal ring of mountains. That ring, now buried under a kilometer of limestone, remains a powerful geological force. It acts as a hidden wall, directing the flow of underground water and creating a unique circle of sinkholes known as cenotes that dot the Yucatan surface like a dotted line drawn by a giant. This subterranean structure dictates where Mayan cities could be built, where modern resorts find their water, and how the entire peninsula's ecosystem functions. A modern map of the region's water sources is, in essence, a map of a 66-million-year-old wound. Planetary geologists study these violent imprints to understand how extraterrestrial forces can remap a planet in an instant. Meteor Crater in Arizona is a pristine classroom for this. A mere 50,000 years old, it shows the process in frozen detail. A bowl excavated from the flat plain, its rim lifted upward, its floor a chaotic jumble of shattered rock. An impact of this scale instantly creates a new mountain range and a new valley where none existed before. On a larger scale, these events can form massive lakes, as the Sudbury Basin in Canada demonstrates, a crater so vast it filled with water and sediment and now holds some of the planet's richest nickel deposits. What other craters lie completely concealed, hidden beneath the forests of the Amazon or the ice sheets of Antarctica? Their discovery continues to redraw our understanding of Earth's turbulent history, reminding us that our geography is sometimes written by random visitors from the cosmos. This role of chance stands in stark contrast to a far more deliberate, human-driven force that is now causing the very ground to sink beneath entire cities. Mexico City is sinking back into the lake it was built upon. The Metropolitan Cathedral tilts at an unsettling angle, and the Angel of Independence monument has required new steps to be built just to reach its base, all because the ground beneath them is collapsing. This is land subsidence, a direct and dramatic consequence of our thirst. The city, constructed atop the drained Lake Texcoco, relies on pumping vast quantities of water from deep aquifers. When this water is removed, the fine clay sediments and porous rock that held it compact like a dried-out sponge, with no space left to rebound. The city is not settling, it is actively sinking, in some areas by over 20 inches a year. This slow-motion collapse forces a constant, costly revision of the city's topographic maps, as surveyors struggle to keep pace with a landscape whose elevation is literally dropping out from under it. Hydrologists see this same story unfolding in urban centers worldwide. Jakarta, Indonesia, is sinking so fast that officials are planning to move the national capital. In California's Central Valley, the relentless pumping of groundwater for agriculture has caused the land to subside by dozens of feet in some places, creating a vast sunken bowl. This human-driven sinking fundamentally alters the geography of risk. Land that was once safely above sea level can be lowered beneath it, permanently expanding flood zones and forcing governments to redraw hazard maps that determine insurance rates and building codes. The very infrastructure meant to support these cities, the pipes and roads and foundations, cracks and fractures under the strain of the shifting earth. How many other bustling metropolises are on a slow, invisible descent, their foundational stability being pumped out from under them gallon by gallon? Our manipulation of water does not just sink the land, however. In other places, other creatures are using that same water to build it back up, acting as nature's most diligent landscape architects. A single beaver can radically redesign a valley. With nothing but instinct and sharp teeth, this rodent fells trees and piles mud and stone to dam a stream. The backed-up water floods the surrounding area, creating a new pond and a rich wetland where a meadow or forest once stood. This is not a minor adjustment, it is a complete geographical overhaul. The beaver pond slows the flow of water, allowing sediment to settle and building up new layers of soil. It raises the local water table, creating a new habitat for fish, amphibians, and birds. A map of a beaver territory is a map of constant, purposeful change, dotted with a series of these engineered wetlands that fundamentally alter the hydrology and ecology of the entire watershed. These animals are ecosystem engineers, a term biologists use for species that create, modify, or maintain habitats. Beavers are not alone in this cartographic role. In the tropics, colonies of leafcutter ants move an immense volume of soil, building elaborate underground cities that aerate the earth and alter nutrient cycles. Coral polyps, as we have seen, build entire islands. Even earthworms, by tirelessly tunneling through the ground, mix soil layers and improve water infiltration, subtly reshaping the very foundation of the landscape. The work of these creatures proves that the power to rewrite the map is not reserved for catastrophic forces or human industry. It is a quiet, persistent process happening all around us, driven by the daily lives of the planet's inhabitants. Their constructions demonstrate that stability in nature is often a dynamic balance, a constant state of construction and revision that we are only just beginning to appreciate. A single beaver can radically redesign a valley. With nothing but instinct and sharp teeth, this rodent fells trees and piles mud and stone to dam a stream. The backed-up water floods the surrounding area, creating a new pond and a rich wetland where a meadow or forest once stood. This is not a minor adjustment, it is a complete geographical overhaul. The beaver pond slows the flow of water, allowing sediment to settle and building up new layers of soil. It raises the local water table, creating a new habitat for fish, amphibians, and birds. A map of a beaver territory is a map of constant, purposeful change, dotted with a series of these engineered wetlands that fundamentally alter the hydrology and ecology of the entire watershed. These animals are ecosystem engineers, a term biologists use for species that create, modify, or maintain habitats. Beavers are not alone in this cartographic role. In the tropics, colonies of leafcutter ants move an immense volume of soil, building elaborate underground cities that aerate the earth and alter nutrient cycles. Coral polyps, as we have seen, build entire islands. Even earthworms, by tirelessly tunneling through the ground, mix soil layers and improve water infiltration, subtly reshaping the very foundation of the landscape. The work of these creatures proves that the power to rewrite the map is not reserved for catastrophic forces or human industry. It is a quiet, persistent process happening all around us, driven by the daily lives of the planet's inhabitants. Their constructions demonstrate that stability in nature is often a dynamic balance, a constant state of construction and revision that we are only just beginning to appreciate. But this gentle engineering stands in stark contrast to another elemental force, one that wields not water and mud but pure, cleansing fire. Fire can rewrite a forest in a single, scorching day. The Yellowstone fires of 1988 were a national trauma, a seemingly unstoppable inferno that blackened over a third of the park's iconic landscape. From the ground, it looked like total destruction, a map of green transformed into a charcoal sketch. Yet that was not the end of the story, but a violent new beginning. The intense heat performed a brutal but necessary service, cracking open the serotinous cones of lodgepole pines and releasing seeds that would not have germinated otherwise. It cleared away decades of dense undergrowth, allowing sunlight to reach a forest floor that soon erupted in a carpet of new wildflowers and grasses, nourished by nutrient-rich ash. The ecological map of the park was not erased, but fundamentally redrawn, creating a mosaic of different aged forests that supported a greater diversity of wildlife than the homogeneous old growth it replaced. Fire ecologists now understand that suppression efforts in the previous century had created a tinderbox, allowing fuel to accumulate to dangerous levels. The Yellowstone event forced a complete rethink of land management, acknowledging that fire is not an enemy to be defeated, but a vital, recurring force in the ecosystem's life cycle. This cycle of destruction and rebirth is known as the Phoenix effect, but its consequences are not always so clearly beneficial. In the fire-prone chaparral of California or the eucalyptus forests of Australia, a blaze can be so intense that it vaporizes the organic matter in the soil, leaving behind a water-repellent layer. When the rains come, the water cannot soak in and instead sheets down the barren slopes, carrying away the topsoil in devastating mudslides that reshape the very contours of the land. These post-fire debris flows can carve new gullies, bury roads under feet of silt, and fundamentally alter watersheds, forcing emergency cartographers to update flood and landslide hazard maps for years after the flames are out. How do we live with a force that can both create and destroy with such ferocity? The challenge is to balance our need for safety with the recognition that fire is one of nature's most powerful and essential landscape architects. Its work, however destructive in the moment, sets the stage for the next act in an endless drama of renewal, a process that begins with the very ground beneath our feet being carried away by wind and water. The soil beneath our food supply is vanishing. During the 1930s, the American Great Plains became a terrifying preview of this, when a combination of deep plowing that tore up the native grasses and a severe drought created the Dust Bowl. The land, stripped of its anchor, simply blew away. Gigantic dust storms blackening the sky for hundreds of miles, scoured the earth down to bare subsoil, turning what were once fertile fields into a barren, cracked desert. This was not just an environmental disaster, it was a human one that violently redrew the map of settlement. Hundreds of thousands of people, their farms and livelihoods literally carried off by the wind, were forced to abandon their homes in a mass migration westward, their desperation etched into the population charts of the era. This catastrophic event demonstrated with brutal clarity that soil erosion is a powerful, if silent, cartographer. It is a process driven by wind and water, where the precious, nutrient-rich topsoil that supports plant life is gradually stripped away. This loss reduces the land's productivity, turning once fertile zones into wastelands. But the impact does not stop at the field's edge. All that eroded soil has to go somewhere, and it often ends up washing into rivers where it accumulates as silt. This sediment can clog river channels, increasing the risk of flooding, and it fills reservoirs, dramatically reducing their water storage capacity and altering the very hydrology of a region. Agronomists and soil scientists work tirelessly to combat this, promoting conservation practices like no-till farming, planting cover crops, and building terraces to hold the earth in place. Yet natural cycles of drought, coupled with the intensifying effects of climate change, continue to degrade soils on a global scale. In Africa's Sahel region, south of the Sahara, a relentless process of desertification is underway, where overgrazing and deforestation are causing the fragile land to lose its vitality, allowing the desert to advance and consume more territory with each passing year. This loss of arable land is a direct threat to food security for millions, but it also forces a constant revision of our maps. The zones we once confidently colored as agricultural heartlands are shrinking, while areas of barren and unproductive land are expanding. What other breadbasket regions, from the plains of Central Asia to the American Midwest, are at risk of seeing their fertility simply blow away? Soil erosion underscores a profound truth that the accuracy of our maps is intimately tied to the health of the land itself. As we lose soil, we are not just losing dirt, we are losing the very ground that defines our geography. And just as the wind and rain reshape the continents, the planet's great oceanic rivers are tirelessly at work sculpting the boundaries where land and water meet. The sea itself is a restless traveler, carrying the land grain by grain to new destinations. Along the California coast, an invisible river flows within the ocean, a powerful current that runs parallel to the shore. Each wave that strikes the beach at an angle pushes countless sand grains sideways, setting in motion a process called longshore drift. This relentless, watery conveyor belt moves immense volumes of sand southward, piling it up to build wide, welcoming beaches in towns like Santa Monica. But for every beach that gains, another loses. Just a few miles down the coast, communities watch their shorelines narrow year after year, starved of the natural sediment that is being carried away. The very shape of the coast, as drawn on any map, is just a temporary snapshot of this endless sediment pilgrimage. Ocean currents are the great planetary circulation system, driven by the wind, the sun's heat, and the spin of the Earth itself. These immense flows do more than just move water, they transport the building blocks of geography. They carry silt from the mouths of mighty rivers, depositing it far out to sea to form vast underwater plains. They bring nutrients from the deep that feed plankton blooms visible from space, and tragically, they also carry our pollution, concentrating plastic waste in slow-moving gyres thousands of miles from any human source. Marine geologists mapping the seafloor see the evidence of this constant motion in the shifting forms of spits, those narrow fingers of land that reach across bays, and in the restless wanderings of barrier islands, which roll landward over centuries like slow-motion waves of sand. A delta, that familiar branching shape where a river meets the sea, is not a fixed landmark. It is a battleground where the river's gift of sediment fights a daily war with the ocean's power to carry it away. Our attempts to control this system often backfire spectacularly. When we build jetties to protect a harbor entrance, we are effectively building a dam across that river of sand. The result is often a stunningly wide beach on one side of the jetty and a desperately eroded coastline on the other, where the natural flow of sediment has been abruptly cut off. These interventions reveal our fundamental misunderstanding of the coast as a permanent line, rather than a dynamic zone of exchange. If the great currents themselves were to shift, which many climate models predict, how would the world's most iconic coastlines be remade? The famous beaches of Rio de Janeiro or the Mediterranean could be stripped bare, while new ones might emerge where none exist today. This fluid power of the ocean to build and destroy, however, pales in comparison to its most violent and immediate act of cartographic revision. A tsunami does not just flood the land, it redraws it. The Indian Ocean tsunami of 2004 did not merely inundate coastlines, it scoured beaches down to bedrock, ripped entire forests out by their roots, and pushed immense carpets of sand and debris miles inland. When the water finally retreated, it left behind a new geography, one where familiar landmarks were gone, river mouths were blocked, and in some cases, whole islands had been permanently tilted, their elevation altered by the sheer force of the subterranean earthquake that spawned the waves. Navigational charts became dangerously inaccurate overnight, and reconstruction efforts had to begin with a brand new, raw map of a fundamentally altered world. These waves are not simply large swells, they are pulses of energy moving through the entire water column, generated when the seafloor itself abruptly shifts during a massive earthquake, a volcanic collapse, or a submarine landslide. As this energy approaches the shallow coast, it transforms into a raging, high-velocity surge that acts like a bulldozer, eroding beaches, undermining cliffs, and drowning coastal ecosystems in salt water. The backwash, as the water drains back to the sea, can be just as destructive, carving new channels and leaving behind temporary lagoons where towns once stood. The work of geologists in the aftermath is a race against time to document a transformed landscape. Their post-tsunami surveys reveal startling vulnerabilities, such as the exposure of ancient mangrove peat layers or the discovery of archaeological ruins that had been hidden for centuries, now laid bare by the waves' scouring power. These findings prove that our current coastlines are often built upon the rubble of past cataclysms. How do we prepare for a force that can remodel a continent's edge in a single morning? The answer lies in accepting that our static maps are a form of fiction, and that true safety requires a dynamic understanding of the coast as a living, changing, and sometimes violently rewritten frontier. All these forces, from the patient creep of continents to the instantaneous violence of a tsunami, point to a single, humbling truth about the world we call